At this point, we've fleshed out our framework for dealing with these statistical inference types of questions. Namely, we've worked with confidence intervals and we've talked about hypothesis testing. For really the rest of the semester, we're going to be doing these types of inference questions, only working with different types of data. So far, we've worked with both categorical and quantitative variables, each time comparing the measurement to some previous baseline. So maybe we have this preconceived notion that 30% of M&Ms are supposed to be green. The variation on this that we're introducing today is that rather than comparing to this previously stated quantity, we're comparing two separate groups. All right, here's our running example. Say that you really like green candy. So we can talk about the percentage of M&Ms that are green. So out of the entire population of M&Ms, some percentage of those candies are green. We're going to call that percentage P1. Similarly, some Skittles are green. So in this context, the quantity in question, the thing that we're interested in, if we are comparing these two groups, if we're comparing M&Ms versus Skittles in the what percentage are green competition, well, we want to be comparing P1 and P2. So rather than having two quantities floating around, the quantity in question is going to be P1 minus P2. And this is going to encapsulate the difference between these proportions. If this number is positive, that means that the percentage of M&Ms that are green is greater than the percentage of Skittles that are green. So this is the quantity in question that we're interested in. And just like before, there are a few different types of questions that we can ask about it. For example, we could run a hypothesis test. Maybe the Skittles company is claiming that their percentage of green candies is better or greater than M&Ms. We could also find a confidence interval for this value. We could say, hey, if I take a sample of each, then, the difference in percentages that are green between our two samples is my best guess for the difference in percentages that are green in the populations. But there's going to be some error bars. We can find confidence intervals for this quantity, just like we did in the past. So let's think about our setup. So some percentage of M&Ms are green, but if we were to take a sample of, let's say, 80 M&Ms and go through and count how many of them are green, well, the answer that we get is going to depend on, which bag of M&Ms we chose. Due to the nature of how a random sample is taken, we expect the proportion of that random sample to be somewhat similar to the proportion of the population. But there's always some amount of variance. So what we have here is the probability distribution for P1 hat. If I take a sample of 80 M&Ms and 60 Skittles, P1 hat is the proportion of M&Ms that are green, whereas P2 hat is the proportion of Skittles that are green. So the way I've drawn this, the percent of Skittles that are green is greater than the percent of M&Ms that are green. That said, if we take a sample of some number of M&Ms and some number of Skittles, it's certainly possible to have a particularly large number of M&Ms that are green and a particularly small number of Skittles that are green. So if the quantity in question, this P1 minus P2, well, this thing should be something negative because P2 is big. The way I've drawn this, because P2 is bigger than P1, but our particular sample might not come to exactly that conclusion because of the nature of taking a random sample. If all that we have to work off of is a single bag of M&Ms and a single bag of Skittles, this is going to give us some idea of the comparison between P1 and P2. But like with just about any statistics concept, there's still some amount of uncertainty. All right, so again, the quantity in question is this P1 minus P2 number, the difference in percentages of M&Ms that are green compared to Skittles that are green. So if we took a sample of each, let's say we take a sample of N1 M&Ms, and maybe we get this proportion that are green, and we take a sample of N2 Skittles, we see that this proportion are green, we can then calculate P1 minus P2 by just subtracting these two samples, and this would correspond to a negative value, so something over here. So we can think about this probability distribution for this P1 hat minus P2 hat quantity. Assuming that we understand P1 and P2, we can find the probability distribution for a single sample from the M&M group or from the Skittle group. But then we can also think about the probability distribution if we were to take a sample from each and then do this calculation, P1 minus P2. Because, again, the way I've drawn it, P2 looks a little bit bigger than P1, more often than not, the answer that we get, the sample that we take, is going to have a negative value for P1 minus P2. But it's certainly possible for the sample of M&Ms that we take to have a greater proportion that are green than the sample of Skittles that we take. And in that situation, this P1 minus P2 hat is something positive. Okay, so we're asking this probability question. We're taking this number P1 for granted, and we're saying if I were to take a sample of size N1, what proportion of that sample do I expect to be green? This is something we've talked about before. The expected value, or the middle of this probability distribution, should be the same as P1. The standard deviation of the probability distribution is the square root of P1 Q1 over N1. Same type of thing holds for this probability distribution for the percentage of Skittles that are green. The question that we're now asking is, how do I take this information and say something about the probability distribution for the difference of these two values? As you might expect, the middle of this distribution should be the difference between these two values. So the expected value in the difference of proportions in our sample should be the same thing as the difference in proportions of our population. The standard deviation for this probability distribution comes from the fact that variances add. We've talked about this before. If we're combining two different distributions, then we can take their variances, so the square of their standard deviations, which would just be this P1 Q1 over N1 term, and we can add those variances. To turn it back into a standard deviation, we then take the square root. So this equation is sort of the Pythagorean theorem of statistics. We're taking each of these terms, squaring them, adding them together, and then square root. You might ask why we add these components while we subtracted for the expected values. The main reason for this discrepancy is that we're talking about two totally different ideas. For expected value, we're talking about the comparative positions between P1 and P2. When we were talking about the difference between them, we're just subtracting these two quantities. Standard deviation is a measure of uncertainty. At least the way I've drawn this, the standard deviation of each of these probability distributions are pretty similar. So subtracting them would mean that they would roughly cancel out, that there would be virtually no uncertainty in this. So if we subtracted these quantities, then they would somewhat cancel each other out, resulting in somehow less uncertainty. Whereas what we're actually doing is that we have more uncertainty going on. Not only is there variance in this first distribution, there's also variance in the second distribution. And so when we're doing both things, we're taking a sample from each side, there is an increase in the total amount of variance. Variance is just about always going to be increasing with the more uncertainty, with the more extra stuff that you're doing. Since we're taking two samples, that's going to increase our uncertainty. It increases our standard deviation. Since variances add, we end up with this formula for the standard deviation for the probability distribution of the difference in sample proportions. So again, this is a probability question. If we know P1 and P2, then this is what we would expect to see. When we're actually doing an inference question, we don't know what P1 and P2 are. This difference in particular is the quantity that we're interested in. The information that we have is all information about the sample. So just like we've done in the past, we're going to use our information that we have from our sample as our best guesses for what P1 and P2 are. So just as we've done in the past, the standard error is our best guess for this probability distribution given the information that we do have. If we're doing an inference question, we have access to what the sample looks like, and the thing that we're interested in is what the population looks like. So we are substituting the population information with our best guesses for those values. All right, so that's about all we're changing when we're now talking about comparing two groups rather than just working with a single group. Really, it's what exactly the format is for our data. So if we want to find something like a confidence interval, this is going to follow the exact same format we've been working with. Remember, the confidence interval is our best guess for what the population is doing given information about the sample. So we think that it's going to be, probably roughly the same as the sample, give or take some amount. So the margin of error is everything after the plus or minus. It's going to be the standard error, so the standard deviation for the probability distribution, times some number of standard deviations, which is dependent on what our confidence level is. This stuff hasn't changed from before. For example, if we want a 95% confidence interval, we need to use 1.96 for z-star. For hypothesis testing, we're now going to call this a two-sample z-test. Last week we worked with only one sample. Now we are comparing two different samples. And I want to again point out that two-sample is different than two-sided. Two-sample means that we're talking, like we've been working with, two different groups. Two-sided is talking about what our alternate hypothesis is. If it's one-sided, we're only considering values greater than or less than our null hypothesis. If it's two-sided, we're considering both directions. Going off of that, our null hypothesis for a two-sample z-test should just about always be that the difference between our two proportions is 0. Our baseline assumption is that nothing special is happening. So if the two groups are really about the same, then the difference between the two of them should be 0. This is just a fancy way of writing P1 equals P2. Like before, our alternate hypothesis is either going to be that this quantity P1 minus P2 is not equal to 0 if it's a two-sided test, or it's going to be that this quantity is greater than or less than 0 if it's a one-sided test. One last note I want to point out for hypothesis testing when working with a two-sample z-test is that when we are talking about our assumptions, we need to make sure that our assumptions hold for each group individually. So not only do we need, for example, the expected number of successes in group 1 to be at least 10, we also need that to be true for group 2. And the same for the other assumptions that we make.